Okay, I am Massimo Fioravanti. I am a compiler researcher at Politecnico of Milano. My research topic focuses on maintaining, refactoring, testing, and reuse hundreds of interactive programs, ideally with as little overhead as possible. And this sounds a bit strange, but let's make an example. So one of the projects we are working on is a collaboration with Vodafone Automotive. And one of the objectives of Vodafone Automotive is the department of Vodafone working on cars. And one of their objectives is, for example, to have machine learning algorithms to predict accidents before they happen. And since corporate will not let us use real humans, we cannot test those algorithms in the wild. And so we need a simulator to train the AI agents and so on. Train the prediction algorithms. And those prediction algorithms require to be, the simulator requires to be configured with a series of interactive scenarios which are designed by domain experts, ideally. And one thing that changed recently, since the advent of machine learning, is that you want the simulators to be as fast as possible. It's not enough that they are as fast enough to be used by a human. You want them to be as fast as possible because if you do more samples, you are happier. Okay, but as a definition of interactive program, we are going to use this definition, that is an interactive component, a subset of a program, not the whole program, is an interactive component if the behavior of the component depends on the action of a user, which might be a human or a machine, and the action of the user depends on the state of the component. Just to make a couple of examples. If you have a website with a multi-page form, say that you have to pay taxes, and the first page asks you if you have children, and then you have to pay different taxes if you have children or not. That is an interactive component because the later pages of the website depends on your inputs, and your inputs depend on the current state of the system. If you have a chess simulation to train AI agents, that is an interactive component because the state of the chess game depends on the action of the AI agent, and the action of the AI agent depends on the current state of the game. If you have the TCP protocol, it is an interactive component because the state of this side of the connection of the TCP protocol depends on what the other guy on the other side of the connection is doing. And what the other guy on the other side of the connection is doing depends on what you are doing on your side of the connection. A load balancing algorithm that spawns and tears down servers, depending on the state of the network, is an interactive component because the load balancer depends on the state of the network, and the state of the network is affected by the behavior of the load balancer. This is a series of often but not always. Right? This is not always true, but often happens that interactive components are part of a larger system. In the example of the car simulator, the interactive scenarios are not the most complex part or the larger part of the system. A single scenario is kind of simple, and the most of the complexity is in the machine learning layer and in the graphical engine layer and so on. And often interactive components are a small part of a programmer job. Most of you probably at least once have written an interactive command line tool, but most of you probably do not spend most of their time thinking about interactive systems. And so the techniques to design, implement, maintain interactive components are not that well known in the wild. And this is the reason for this talk, to have a place I can refer people to, in particular my students, when they have never seen these ideas. Another thing to notice is that often interactive components are mandated by business requirements and or third-party specification documents. If you have to implement the TCP protocol, you will have to implement it as written in the specifications. You will not implement TCP wrong because it's faster. And in the case of the car simulator, we have to implement the scenarios as specified by the domain expert. We will not decide, this car is too difficult to implement, we will skip it, and will not implement it. And then, as all systems, they start with simple complexity, and then they grow in complexity until they become more complex. And these 4 points together means that often people end up designing a system that is that works when it's small, but then breaks when it's large, and requires those people to entirely rewrite the system from scratch, when if they knew the correct way the way to do it from the start, they would not have needed to rewrite it. Okay, throughout this presentation, we will use this running example. It's very small, and it is an interactive sequence where a user is allowed to roll 2 dices, sum the result of the dices. If the result is less than 7, and the user wants to reroll, then you reroll the dices. If the user does not want to reroll, or the result is more than 7, instead the user is allowed to add an arbitrary quantity between 0 and 5 to the result. This makes no sense, but this was the only thing I could fit on a slide, so we have to run on with this. And here we have actions. User wants to reroll, and user decided quantity are user actions. And everything else is regular code. Rolling 2 dice is a random event, but it is not a user action. It's performed independently from the user. And this is a small example. In practice, you expect that the action one can take are very, very large. So you pretend that there are hundreds of actions you can take. So what is the problem with interactive components? The issue with the interactive components is thread blocking. In the running example, when you reach the line user wants to reroll, the thread will stop until the user has provided the information you need. There is no way around it with this implementation. You cannot skip the fact that you have to wait for the user to provide the data. And blocking is often unacceptable, and spawning a thread sometimes it's too costly. Right? If you can for machine learning, if you can skip creating a thread, you are happier, but sometimes you are forced. So let's make examples of places where you cannot block the simulation, the interactive component. If you have a graphical engines often, practically always, take over the main loop. They take over the main loop because they must provide 60 frames per second or whatever they want. And so the code for the graphical engine has the main loop, and it will be something like, while the engine is not done, you render and display a frame, you go from the state of the simulation, you produce an image, and you put the image on screen. And this step if you want to implement rendering as an interactive step, you can do it. But in practice, rendering is not interactive. It is a conceptually pure function that goes from the state of the simulation to an image, and that is done. Querying the inputs, it is interactive when you query the inputs, you check if every key of the keyboard has been pressed, and if it has been pressed, you register that it has been pressed. This is what typically people think about being interactive, but this is does not meet the definition we gave before. Right? The definition we gave before was the system depends on the user input, and the user input depends on the system, while querying the inputs only depends on user input, but the user does not care about what is happening about their inputs. And so the only place that is left that is actually interactive, it is the simulation. Like when you perform the simulation step, that you go from the current state of the simulation, say the current state of chess, to the next state of chess. And that is the simulation step. And that cannot be blocking because the engine has the main loop, and you cannot stop there waiting for an input. The machine learning example is in the same category. if you have a machine learning component that is learning to play chess, you say, while the game is not done, the neural network will select a move depending on the current state of the game. And then you will apply the move to the game state, and you will transition the game state to the next state of chess. Selecting an action is not interactive because the machine learning, in this particular case, let's say the machine learning agent is stateless. So it's a pure function that is going from the current state of chess to the best possible move of chess. So it's not interactive. And the interactive component is the logic of the game. Well, you say, okay, that is easy. What do? You rewrite the system as a class. Right? You have the function, you just extract, on the left there is the original running example, on the right there is the implementation, the same implementation written as a class. You have the variable result, which is what the user cares about. You have the start function that will start the simulation. And you have the next variable. The next variable will tell us where we want to go next. Right? We say, are we at when we perform start, we say, are we in state, is next equal to 0? If next is equal to 0, we are in the correct state. We can perform start. We roll the two dices, and we set next, depending on the result, we say if the result is less than 7, we set next to be equal to 1, or 2 if it is not. And then the other two functions, user rerolls and user decides quantity, check if they are in the state next equal to 1, or in state next equal to 2. And if they are, then they are in the correct state. You can perform the action. What happened? You can perform the action. If the user wants to reroll, you do reroll, and you set next to be correct to -1 to say that you are done if the user did reroll, or to 2 if the user did not want to reroll. And user decided quantity adds a q to the result, the argument to the result, and then next is equal to 1. Okay, but now what did we do to perform this transformation? Like we went from the class implementation, from the function implementation of an interactive system to the class implementation of an interactive system. And there are questions we might wonder, right? We may wonder, can we do this automatically? Do we have to do it by hand? Is it possible to do it automatically and so on? And I want you to, and if you have done it before, you will know that what you do is that you start removing control flow, right? Here, the if function that checked the result disappeared. This if disappeared because we rewritten it as an assignment of a variable. And then if there were more nested control flow stuff, they would have to disappear as well so that we can rewrite it as a class. And then we manage the variable next to tell us where we want to go. But managing the variable next, and I want to think about this, managing the variable next to say where we want to go, how is it conceptually different than using a goto? It's different because that's different things, of course, right? But you are still managing where you want to go explicitly. You have to place the assignment of next, and you have to place the assert that you are in the right spot. And that is the same for a goto and a label. And so if you are a bit insane, you start thinking that maybe the next variable, managing the next variable is like managing unstructured C code, where you say, I want to go to this label, or I want to perform, well, you can perform a switch if you want. Setting next to -1 is like performing a return, and so on. And the conclusion you notice at some point, let's talk about this later, is that when you want to answer the question, can any arbitrary blocking function, interactive blocking function, be rewritten as a class? The answer is yes. And is there a general algorithm that converts a function into a class? Yes, and that algorithm is performed by compilers. In compilers, it's called control flow flattening. When the same algorithm you do in your mind to turn a function into a class, it is the same algorithm that the compilers do to turn your code into assembly, conceptually. And it is the same algorithm that hardware design tools use to turn high-level code into state machine, and it's called state machine synthesis. And so the next question is, if the compilers knows how to do it, can GCC, Clang, or MSVC do it for us? Yes, but only if coroutines are enough for your problem. Okay, now there is a coroutine digression. So what do coroutines do? Coroutines do exactly what we wanted, right? Coroutines let you suspend a program without creating a thread. And under the hood, the compiler is doing exactly the transformation we want to do by hand. On the left, there is the running example written as a coroutine. The running example written as a coroutine contains 2 extra arguments, and then contains co-await that will suspend the coroutine. Let's ignore, the 2 extra arguments are a bit strange, but what is important is that you can use it to inject content into the coroutine. And on the right, there is the main that will execute the coroutine. The coroutine, the main will allocate the 2 mechanisms to inject values into the coroutine, will allocate the running example, will start the running example, and when you start the running example, you will go from the start of the running example, you will execute roll 2 dices. If the result is less than 7, you will co-await reroll. Co-await reroll means that you will stop the execution of the coroutine, and you will wait until someone from outside invokes reroll.supply. So you will go back to t.start. You will perform reroll.supply. You will pass false to the coroutine. The reroll inside is the same reroll as outside. You will resume from this reroll. You will resume from the co-await. False will be passed to the co-await. The co-await will pass it to do reroll. If the user does want to reroll, that is false. So you do not take this if statement. You jump to the end. You do result plus equal to co-await. You co-await on quantity. You stop the execution of the coroutine. You go back to reroll.supply, which is now terminated. You perform quantity.supply. You pass free to quantity. Quantity pass it back to co-await, and the result is plus equal to free. This is what we wanted, right? We have not performed the cluster write. We have used coroutines. And coroutines are uncomfortable to use, to be honest. But that is what we have at the moment. And the issue is that C++ coroutines are actually not copyable or serializable. And that is a limitation. If your system requires copying or serializing the state, like if you want to do it, use it for machine learning, you want to implement chess, and you want to send the state of chess to the machine learning stack, you must serialize it, and you cannot do it if you implement it as a coroutine, because coroutines are not serializable. Copyable and serializable coroutines are with zero overhead and everything you want, are a very challenging thing to implement. If you are interested in this particular thing, talk to me afterward, because we have looked into it a lot. But what we care about is that the conclusion of the original scene is that some use cases require you to give up the main loop, and the interactive component cannot have it. If the interactive component cannot have it, either you have to spawn a thread to be in another thread, but that is costly, but it is simple. You can explain to someone how a thread works. You can use coroutines, which are fairly, they kind of takes 1 malloc and 3 per coroutine creation, which can be manually avoided. You can do some shenanigans to remove it. And they are complex at the start, but once someone else set them up for you, because you don't want to do it yourself, they are fairly easy to do afterward. But they are not copyable or serializable. Rewriting it as a class takes one extra integer most of the times. It's very cheap if you do the translation to the class corrector. And they are very easy when the program is small, but if the program grows to hundreds of user actions, it becomes very difficult to manage. And the other thing to notice is that when you have performed the rewriting, when you rewrite the system to not block and to be serializable, the domain expert in your company will still think about the non-blocking the blocking version, right? It does not. Your domain expert does not think about threads and so on typically. And so they will think in a way of in an implementation, and your implementation will be different. And you will have to manage every time they want a modification, you will have to remember how it is implemented, and every time you have bugs, you have to figure out how they mapped on the original on the original version that is the one in the mind of the designers. Okay, but then now what we want to do is to categorize all possible programs and figure out an acceptable implementation that is zero overhead, ideally, an ideally zero overhead implementation that either is non-serializable if you do not care about serialization, right? Which are situations in which you do not care about serialization. If you have a protocol, as we said, is an interactive component, but a protocol, you do not want to serialize the state of a protocol, right? If you save on disk the state of a protocol and then you load it back, the other guy on the other side of the connection is gone. It makes no sense to serialize a protocol. So for protocols, coroutines are perfect, right? That is the exact place where you see coroutines shine. But then if you need serializable systems, you have to categorize them depending on the complexity of what you want to do. So this table is organized left to right in a growing complexity of programs. So a program with no calls is a subset of programs with no recursion that are a subset of recursive programs that are a subset of Turing-complete programs. I will explain what they mean exactly, do not worry. But now we want to find a solution that works for every of these situations. And one thing to notice is that domain experts often lie. Right? They will tell you, no, we will never need to copy the state of a simulation. For example, they will tell you, no, we will never need to copy the state of the behavior of the car in the car simulator. And then they will tell you, you know what? I want to stop whatever the car is doing, change the behavior of the car somehow, and then after a while restore the state before restore the state before doing the changes. And that requires to copy the interactive component. I mean, maybe you can figure out how to do it without it, but if you can copy it, it's much, much easier. And the other thing is that often you want to isolate user actions in different functions, just because that it makes it easier to manage. And so things often tend to drift. Right? They start somewhere on this image, and then they drift into non-recursive serializable systems. And so you probably, if you need serialization, you probably want to start there often. Okay, let's talk about Turing-complete interactive programs, because it's very quick. Turing-complete interactive programs are interactive systems where the user can provide any arbitrary program as an input to your system. The Python interpreter is a Turing-complete interactive program because you can provide any Python program to the interpreter. If you have a C++ video game that is moddable, like the user can provide mods to alter the behavior, that is a Turing-complete interactive program because the behavior of the system changes at runtime. If you are in that situation, you need an interpreter or just-in-time compiler. I will not explain it how to do it. You will have to watch another talk because it's a bit out of scope. Okay, for the last three blocks, which are the one we are actually interested in, we have to figure out a solution that minimizes the distance, the mental distance between what the domain experts are thinking about and what the implementation does. Because if that is different, you end up having troubles maintaining it. If you care about it, maybe you don't care about it. If you care about it, you want to have as little overhead as possible. And the other thing you want to have is theoretical guarantees that whatever your solution is will be able to scale when you add extra stuff. You do not want a solution that when you add another feature, you have to rewrite entirely because it does not support whatever you want to do. And state machines with some extra tricks are what we want. And now we will talk about state machines for the rest of the presentation. I'm not trying to sell you a state machine. You are better off finding either writing you a state machine library yourself, it is easy, or using a state machine off the internet, find someone that works. But for implementing state machines, it's actually where C++ shines, because C++ can do some tricks which are very interesting that you cannot do in other languages. Well, you can do it in C, probably. That lets you implement state machines very efficiently. So just to recap, a state machine is like a graph. Like you have a control flow diagram. You have a control flow diagram with a start and some exits. In this case, we have 2 exits, and then you have transitions depending on the Boolean expressions that tells you where to go next depending on the current state. This state machine is the same one as the original one. It is still the running example. And in this case, we are talking about interactive components that have no calls. It does not mean that there are no functions. It's not just a big function for the entire program. It means that all the actions, all the user actions, appear in a single function. They do not appear in any other part of the program. And in this case, this is the case. Because user wants to reroll and user decided quantity are 2 user actions. They all appear within a single function. And then everything, and then roll 2 dices is not a user action. It's not a user action, can be a function, and can invoke whatever it wants. It's not a problem. This situation is common, but as we said before, sometimes you want to go beyond it because you want to isolate functions. You want to isolate the user actions in their own functions just because of isolation of concerns. You just separate them to separate them for separate them sake. And now we will see C++ tricks, I guess. How can you implement a state machine? You can do it with switches, but if you do it with switches, depending on the scenario, you might lose performances. You want to mix switches and labels and to use go-tos on the fly. We have a macro called state machine. It is a possible implementation. It's not the only possible implementation. The macro state machine gets expanded into a function called resume that contains a switch. Then we have the macro called state, and the macro called state declares that here there is a state. And the macro called state will contain both a label and a case, so that we can go to the label with the go-tos, and we can go to the case with the switch. And so we have 2 ways to go in that place, where we want to go to state S1. We have next, and next will become a go-to, that will tell us we go to this place. But the interesting part is the part about decisions. Decisions are the points where the user can provide an action. So in this case, state S2 was user wants to reroll. When we enter this state, we have to figure out if the user wants to reroll or not, and we must suspend the execution. And the trick we are going to do is that we place a label. After the label, we set the state to S2. we return from the current function. The current function stops. But then there is the case for S2. And when the user wants to resume this function, it will invoke a resume. It will take the switch. The switch will be over state. The state will be equal to S2. And we will jump back into the case. We will jump back after the decision. And so this way, we have a way to stop the execution and resume it whenever we want. Now the code becomes very large, I'm sorry. But on the left, there is, again, the same implementation as the starting one. We say, we roll 2 dices. We set the result to be the result of rolling 2 dices. If the result is less than 7, we go to state S2. Otherwise, we go to state S4. In state S2, there is a decision. Here, we stop the execution, and we go back to wherever we were before executing this function. And then from here, we expect that the user will provide user wants to reroll somehow. If user wants to reroll, we go to state S3. Otherwise, we go to state S4. If we go to state S3, the result becomes equal to rolling the dice again, because the user did want to roll. Otherwise, we go to the next decision. The execution stops again. We expect for the user to provide a user-decided quantity. And when the user provides user-decided quantity and calls resume again, we can sum the user-decided quantity to the result, and then we go to the end, not that end. On the right, there is the extra content of the state machine. There is the declaration of the possible states. There is the enum for all the possible states. There is the current state. We are using a single integer for the state. There is the integer that is of interest. There is the result integer that is requested by the user. Right? That we cannot omit the result because the user wants the result. And then we have another macro that declares the actions. And this macro gets expanded in this pattern. We declare the action do reroll that accepts if the user wants to reroll or not. We assert that we are in the correct state. If we are in the correct state, we save somewhere. This is not optimal. I know this is not optimal, but the optimal solution did not fit on the slides. And online, I placed the optimal version that saves this bool. It saves somewhere the action that the user wants to do, and then resumes. When we resumes, we know for sure that state is equal to 2. So when we take the switch will jump to case 2. The switch will jump to this case, and then we check if the user wants to reroll, we go to label S4, otherwise we go to label S3. This is extremely convoluted. It's not something you find in the wild. It's very ugly, but the guarantee you get from this stuff is that as long as, let's go here. As long as you want a serializable system that has no calls, that all user actions are within a single function, you get the property that will always scale, will require always a single integer, and whatever you do, you will be able to implement it. But of course, we said it is not a good solution because you often want to isolate things into functions just because of isolation of concerns, just for that reason. And so we end up in the second category, the category where you want a serializable system that contains that contains calls, but they are not recursive. And that's an interactive system that is with calls that is not recursive is an interactive system where you have multiple functions where they can contain actions. So here the red code is user actions. We have 3 functions: caller 1, the running example, which is the usual running example, and caller 2, that contains multiple calls and multiple user actions. And some of the calls of caller 1 and caller 2 end up into running example. Here you have multiple functions with user actions, and so it is, but they are not recursive. No function ever calls itself. So it is a non-recursive interactive system that can be serialized. And this, I think, is the most, if you need a serializable system, this is the most common scenario you end up in. And when you are in this situation, you can reuse the previous solution, but you add an extra trick. And the extra trick is other two macros, and these other two macros are call and return. Call will accept a label to go at, the place you want to go, and a label to remember where the call was. When you want to perform the label, when you want to perform the call, you push in a stack of return addresses the place C1, and C1 is the place after this call. You go to the running example, and then you put the label so that when you are done with the running example, you can go back to this place. And the return, and the trick is now that the original switch that switched over the state is now wrapped into a while true. It's wrapped into a while true. And when you want to perform the return, you take the return address from the state. You set the current state as the last element of the stack of return addresses. You remove from the stack the last element because it's gone, and then you take a continue. You take a continue, you go back to the while true, you perform the switch, and the switch will jump to state. State is equal to C1, because it was the last element of the return addresses, and you go back to case C1. And so in this way, we have implemented fake calls. We are kind of emulating a call stack. And this trick costs us at most one integer plus one integer for each function of the system. At most, because the return address will never, the return addresses stack will never contain more than one return address for each guy, for each function of your system. So it's very cheap. Again, it's very ugly, but you get that as long as you do not introduce recursion, or Turing completeness, you can handle every system you want at any scale without incurring in, without being forced to rework it somehow. And finally, we have the fully recursive system, which I will just briefly mention. The fully recursive system, you replace, instead of having a stack of return addresses, you have a full stack of frames that contain a copy of, every time you want to perform a call, you create another stack frame, which is kind of tricky because you must guarantee, for example, you must guarantee pointer stability, so this is not super easy to do. And I do not recommend this solution. The only place I ever seen this complexity was in particular video games, where the video games was trying to get the user to perform very tricky actions, and those tricky actions were recursive. That is the only place I ever seen it. So I do not recommend to implement this thing if you need it. Okay, and so the final decision tree is, do you need to implement a Turing-complete interactive system? Yes, you need an interpreter or a just-in-time compiler. No. Do you have any reason now or in the future to make the state serializable? If not, you can use a coroutine or a thread. Do you have any reason, do you want, in the future you plan to make it serializable or copyable and you need performances? If you need recursive functions, then you need a state machines with recursive functions. Otherwise, you can use a state machine with non-recursive calls. Okay, and we are at the end. And the conclusion are, non-blocking interactive system force you into a structured control flow. If you do not believe that unstructured control flow is bad, like if you say, I very like unstructured control flow, then whatever solution you're doing, it's fine. But if you believe that unstructured control flow is not optimal, and you believe that is something you believe automatically if you think that coroutines are useful. If you think that coroutines are useful, then you do not believe that unstructured control flow is good. The compilers know how to handle coroutines, but will not do it for you if you need a serializable or copyable object. And I think this is criminal from the point of view from the compiler. Like, it's right there. It's almost capable to do it, but will not do it. And if it was able to do it, all complexity of this presentation would vanish. Like, everything will not. You will not need to think about this any day of the week, and I would be very happy if that was the case. And if you are in that unfortunate situation in which you need these features, and you want to have theoretical guarantees that you will not have to rewrite the system, then you need state machines of various complexity. That's it. You can find the slides and the full code of snippets that implement what I show you with links to Godbolt on that link. That's it. If you have any questions, I'm here.
Hi. Just a quick comment first. The STD rotate, at least the way it's implemented in elements of programming, is a very pretty state machine on GoTos. Very pretty. Okay, so the second question is kind of like, do you think that coroutines can represent every state machine? I've seen quite a bit of state machines, and I've seen quite a bit of functions, and they're not the same thing. And state machines are perfectly valid, reasonable code, but it's not necessarily a function state.
No, okay, yes. Well, you have to be formal, you have that theorem about spaghetti code where you can implement, every function can implement any program. So you have that thing. The question is it there is some problems about type checking. The paper I mentioned before was about exploring the limitation of theoretical type checking in compilers, what compilers can implement, and there are limitations there. And then there is the final question if it is a good idea. When is it a good idea to use coroutines for everything? And the answer is that, again, if you would, to make them work very well, you will need some extra tricks that are not currently there. Like you will need some extra syntactic sugar to express some concepts. Like for example, a concept that you want to express often is not a C++ concept. A conceptual thing you want to express often is preconditions. Like if you implement chess, you want to the coroutine and implement it as a coroutine. You want the coroutine to express the fact that some actions are not valid. Currently, that is not implemented at all. It will not be implementable in C++. So no, in general, no. Coroutines are not optimal to do most things. State machines are better to do many other things. And finally, there are some particular things specific to domains where you are better off writing the class by hand. But you have to know before your domain. If you are in the general situation, like we are with Vodafone, where they send us random requirements, we need a general solution.
If someone wanted to dig deeper into these things, could you provide a bibliography or some reference to books, articles, or whatever you think is
No, the problem is that,
yes,
the question was if there are books about this. And the problem is that the books about, there are the books, but the books are about parsers. Right? Because if you think about it, an interactive system that is requiring user actions, it is accepting sentences of actions. And those sentences of actions are like recognizing a language. And so you are writing a parser, a suspendable parser. And that is sad. But the best thing there is about this, the best thing I ever found is reconciling these ideas to parsers. But this That's it. I'm sorry. There is a question from over there.
I take it. So basically, it's like in this way you can create like a testing framework for an interactive HMI, if I could say. Because it's a series of interactive actions, like pressing in buttons for like an HMI.
Okay, yeah, for example, if you implement one thing we did with this stuff is, for example, we have the implementation of, well, I mean, if you do this stuff and you have knowledge about the preconditions of actions, you know all the arguments that are acceptable to a given action, you know the full transition space of the entire program. You know all the way the user can travel the program. And if the program is deterministic, if the program is random, it's more difficult. But if the program is deterministic, you get a lot of incredible properties. You get the ability to replay from scratch all the user actions. You get the ability to explore all the state of the system, doing an exploration of the state of the system by saving the current state, copying it, performing an action, checking wherever you ended up. And for example, in this way, you can, if the interactive system is small, you can fully explore all possible states and fully prove that the system will not crash.
At compile time. Well, no, not at compile time, but still.
At test time.
At test time, yes.
Yes. I mean, if you want to do it at compile time.
Other questions? No? Okay. So thanks again. Thanks a lot.
Thank you.